Hi, everyone. Hola, Malaga. Thanks for coming to my talk on Vinci, pumping streams into RocksDB and DuckDB. My name is Felix. I'm a committer on the open source Venice project that I'll talk about today, and I've worked on a bunch of other data infrastructure projects over the years. This is my talk in a nutshell. We will be peeling the layers of this metaphorical onion, going from the outside in. We'll talk in general about data to set the stage, then zoom in on a specific kind of data that I call derived data. After that, I'll tell you about Venice, which is a database specialized in serving derived data. And then we'll transition to Vinci, which is one of the client libraries for accessing data in the Venice ecosystem. And we'll get to the deepest layer of this onion, which is the nitty-gritty details of the storage engines that we support. So let's start with data. And in particular, I want to set the context by talking about primary data first. Some related terms that you probably heard of, source of truth, system of record. Here is my own attempt at a formal definition of what primary data is. I say that it is data that's been created or mutated as a direct result of a user action. And here I put the emphasis on direct for reasons that should become clear in the next few slides. Some examples of primary data include the stuff that users write on their profiles on a social network site, the posts that they write on a blogging platform or a newsletter, the messages that they send between users. All of these are user-generated primary data. And now, let's compare and contrast that with derived data. So we can say that derived data is derived from other data, but that's not a very satisfying definition, right? It's too circular. So what does it mean to be derived? It means that it's processed from other data, computed from other data. It could be a superficial transformation, like just some massaging or reformatting to optimize it for a different use case. Or it could be a very significant transformation, as is the case in, let's say, ML inference workloads, where the input is completely indistinguishable from the output, right? So all of these are examples of derivation. The key thing is that derived data is indirect, or you could say it is machine-generated, not user-generated, right? And because it is processed, it often comes from a batch processing framework or a stream processing framework. And in some cases, it comes from both of these. And we sometimes call this pattern of merging batch and real-time data a lambda architecture or kappa architecture. I'll talk about both of these later in the talk. Some examples of derived data use cases include OLAP, meaning online analytics, search, machine learning features, and there are others, but I'll talk about these three in the talk. I gave a whole talk on this previously called What is Derived Data and Do You Have Any? So you can look that up and watch the replay if you're curious. But for now, let's talk about the lambda architecture that I mentioned a moment ago. Some of you may be familiar with it. It's a fairly old concept by now, but let's recap just in case. The idea was proposed by Nathan Mars around 15 years ago, and it says basically the following. We have real-time data sources, which could be the data coming out of a stream processor, for example, and we have batch data sources, which come out of, let's say, a batch processing job. And we would like an online application to be able to access the data coming out of both of these data sources, right? But, and Nathan Mars says, the data sources are sufficiently different that we need kind of like two specialized databases, one for each of the data sources. So the real-time data source will pump its data into a real-time database, which might be kind of like your traditional database where you can mutate individual rows one at a time. And then the batch database is a bit different. It's going to be optimized for bulk loading entire data sets and swapping them in place. And these are more like read-only, immutable data sets. And then the application will query both of these databases in parallel. And if it finds a record in both sides, then it will need to have some sort of read reconciliation logic, right? There could be a variety of policies for doing that, but let's say an example is you look at the timestamp in both of the records and pick the highest one. So that works, and it's been used in production by many companies for a bunch of use cases, including at LinkedIn. But we think we can do better, and in fact, we have been doing better for years now, I would say. But why? What's the downside, right? So the downside is that because the application needs to interact with two databases, well, there is one more moving part than absolutely necessary here, and therefore, the availability is going to be the worst of the two databases, and the latency is going to be the slowest of the two databases, inevitably, right? The weakest link in the chain determines its strength, basically. So what is the alternative? Well, the alternative is what I call the hybrid store design pattern. And I'm going to explain that to you in a minute, but I just want to say we have implemented at LinkedIn the hybrid store design pattern in at least 3 different data systems, including, but not only, Venice. And there are examples outside of LinkedIn as well. As a matter of fact, Pinterest came up with a talk last week where they discussed their KV store system, which also implements that pattern. And we never talked to them about it, right? They did it on their own. So let's talk about what is this design pattern, right? So to explain it, I'm going to walk you through a 4-step process that explains how do we orchestrate the ingestion of a batch data set that needs to be refreshed, right? So in this first step here, we have the initial steady state. So there is a real-time data source, but importantly, you can see that it's not directly writing into the database. Right? It is instead writing into this intermediate, like, staging area, you could say, which we call the real-time buffer. You can think of the real-time buffer as just a regular Kafka topic, basically, right? Just a queue. And there is a process which consumes events from the real-time buffer and applies them to the data set. And finally, the last piece of this is that there is a current version pointer which points to a specific version of the data set. You can think of this like a symlink pointing to a directory, right? And in the initial steady state that I'm presenting here, there's just a single version of the data set, so of course it's the current. The idea here is that if the user issues a read query to this system, they will always get that query served from the current version, right? So now let's move on to step 2, which is that the batch data source now produces a new version of the data set, right? So what happens then is the system will dynamically instantiate a new version of the data set that I'm calling n+1. We can also call it the future version. And at this point, I draw your attention to the fact that the current version pointer has not changed. So from the user's perspective, everything so far is happening in the background. They're still getting their queries served from the content of version n. At some point, the bulk loading of the batch data finishes successfully. And then we enter the next step, 3 out of 4, which is the real-time buffer replay phase. And what happens here is that we seek to some time in the past within the real-time buffer. And now you can start to see why is it that we have this buffer in the first place, right? So this look-back period within the real-time buffer can be configurable, but let's say for the sake of the example, we configure it to 24 hours. So that means we will replay the last 24 hours of write operations that landed in the real-time buffer, consume from there and up to now, right? And apply all of these to dataset version n+1. And again, at this point, I still bring your attention to the fact that the current version pointer has still not changed. So everything so far is still happening in the background. The user doesn't see this or even know about it. And finally, at some point, the real-time buffer replay catches up. And that is when we consider version n+1 to be ready to serve. And that is when, finally, the current version pointer swaps from n to n+1. At that point, n+1 becomes the current version. And version N, which was previously the current version, now becomes a backup version, and we can retain that for some amount of time. We could even roll back to the backup version if we wanted to, let's say if we detect data quality issues in version N+1. And in this new steady state we have here, the real-time write operations are continuing to get applied to all active dataset versions, right? So that's the hybrid store design pattern in a nutshell. And so let's compare that to the Lambda architecture as it is traditionally presented, right? So both of these are solutions for merging batch data sources with real-time data sources. And the key difference is that in the Lambda architecture as traditionally presented, the merging happens at read time, whereas in the hybrid store design pattern, it happens before that, at write time. And from there, all the other trade-offs kind of follow along. Because you have an extra moving part in the Lambda architecture, you have the worst of both availabilities and slowest of both latencies. Whereas in the hybrid store, you have just a single moving part as far as the database piece is concerned. And so therefore, it's better in terms of availability and latency. So now, I want to make that a bit more concrete by talking about Venice, which is one of the derived data systems we have at LinkedIn. Venice has been running in production more than 8 years at LinkedIn. We've open sourced it a little less than 3 years ago. It hosts more than 2,600 production data sets, mostly in the space of online inference, machine learning inference. A lot of the use cases are recommender systems, and I'll give a couple of examples. There are also classification use cases, and even some non-AI use cases as well are hosted in Venice. An example is the feed. So when you load the application or the website, you can see the feed, which is made up of a bunch of posts that come from your network, but your network produces too many posts for us to show all of them to you. So we try our best to pick and choose what we think are the most relevant ones for you personally. So the feed is a recommender system which recommends posts. Another example is people you may know. So this is a use case where we look at the second-degree connections in your network, and we try to guess which of these do you actually know in real life. And so if you were to send them a connection request, they would be likely to accept it, right? So this is a recommender system which recommends connections. A bunch more recommender systems sprinkled throughout the whole site. I gave a whole talk on this that you can watch the replay for if you're interested in learning more. It's called People You May Know, Fast Recommendations Over Massive Data. But moving on, I want to circle back to the hybrid store design pattern and now talk about some Venice-specific implementation details, right? Because there's a bunch of different ways of implementing this pattern. And I think some of those details are interesting for the next portion of the talk. So let's start on the left-hand side and discuss which data sources are supported by Venice, right? So in terms of batch data sources, the most common one are the output of batch processing jobs. So these can be your typical like Apache Spark job, or they could be like Hive queries or Trino queries, or any batch processing framework you'd like. Another case, which is a bit more interesting, or that at least people might not have heard of, is stream reprocessing jobs. So what is that? Well, this is an idea that's been proposed by Jay Krebs in a 2014 blog post that he called Questioning the Lambda Architecture. And in that post, he basically says, it's kind of a bummer to need to maintain a batch processing stack and a stream processing stack, and then you have two code bases, and maybe they'll get out of sync, and you have like double the maintenance burden and all that stuff. So why not instead use just a stream processing job? Then you can maintain a single code base, but you could run it in real-time mode or in batch mode, and this will be just a configuration change, right? So that's the gist of it. And that's essentially the idea that he calls the Kappa architecture. And in Venice, we've built our implementation of the hybrid store design pattern such that we can support both styles, right? So you can choose to have a separate processing stack for your batch and your stream processing, or you can choose to use the same stack and we'll make it work either way. In terms of real-time data sources, the most common one are stream processing jobs. So these can be like your Apache Flink, Apache Samza, Apache Beam, whatever stream processing technology you wish to use. And those jobs will pump events into the real-time buffer topic. Another case is incremental push jobs. So those are actually batch processing jobs, but instead of producing a full snapshot of like the whole data set, they produce just a smaller delta. And the user would like this delta not to get swapped in instead of everything else that's already there, but they would like this delta to be applied additively to the existing data set. So we make it go through the real-time path like all the other sources. And we have, that's a fairly popular use case as well. The third category are online producers, and this is just a simple library that you can have in any online application, and it will allow you to write events to the real-time buffer topic without being within the runtime of a batch processing job or a stream processing job. And you can mix and match any of these real-time data sources in the same Venice store if you'd like. In terms of write operations that we support, we have put, delete, and update. Put and delete are what we can call full row operations. So, for a given key, change the content of the whole row, or for a given key, delete that row. Whereas update operates at a more granular level, as you might expect. You can, for a given key, update the value of some of the columns only. Or if these columns are nested collection types, like maps or sets, you can manipulate the content of these collections, like add items into them, remove items from them. The key thing is that with update, you don't need to know what the rest of the row contained or what the rest of the collection contained. You just declare your intent, and you delegate to Venice the responsibility of merging that into whatever is already there. Now, for this next part, I want to zoom in on these two components, the real-time buffer topic and one of the dataset versions, right? So what I'm about to present actually exists separately for each dataset version that are active in the system. So this happens independently for each of the version. So if we explode this like little database icon here, which essentially represents the Venice server in a sense, internally we got these sort of three components. So within the Venice servers, we have many replicas of the data, right? For a given partition of the data, we have at most one leader replica, and then the rest are follower replicas. And these have different roles and responsibilities. So the leader replica is the one that consumes the real-time buffer topic, which, as I've been saying, contains put, delete, and update operations. And it will process those operations by performing a read, modify, write sequence. So it reads its local state, which is in RocksDB. I'll talk more about RocksDB later. And it merges the content of the incoming write operation into whatever it finds that's already there. And then that results in the output, we could say. And this output row is then stored back into the local state of the server, as well as in a second topic, which we call the version topic. And importantly, as you can see, the version topic is guaranteed to not contain any updates. So it only contains these full row operations. And that's important because we want the follower replicas, who are the ones consuming the version topic, to be capable of blindly applying these operations. So that makes the workload of the followers cheaper because they don't need to perform the read, modify, write. Another responsibility of the leader is that it performs replication. So Venice is a multi-region system. And here I'm going to present like what two regions would look like. So in the bottom row, the green icons are like, let's say, region A, and the red icons at the top are region B. And there is actually a leader replica in each of the region, right? And they're independent from one another. The leader consumes not a single real-time buffer topic, but rather it consumes a local real-time buffer topic and one remote real-time buffer topic for each of the remote regions. And so because it consumes multiple inputs like this, it actually can consume events in a different order than the leader in the other region, right? And therefore, we need, we want to have a deterministic outcome, right? And so in addition to performing the read, modify, write, the leader is also going to do deterministic conflict resolution. And for that, we use CRDTs, conflict-free replicated data types. Now, switching gears away from the write path of Venice, let's talk briefly about how is data read from Venice after it lands there, right? So we have this Venice client library, which is capable of issuing queries across the network to the servers. And in Venice, we made the design choice that all replicas will serve read traffic. So this is an abidability-oriented system, and consistency is always eventual. In addition to helping with availability, the replicas can also help with read scaling. So for very high throughput use cases, we provision them with a higher replication factor. The APIs that we support are kind of a variety of paradigms. We started off as a key value store, so we have single get, batch get. But then we added some document store-like functionality, so you can project individual fields of the records or individual columns of the rows. And there is even a little bit of vector math functions that you can push down into the server to make some ML use cases more efficient. But all that works great for more than 2,000 data sets in production today. But what if it's not good enough, right? So that's where DaVinci comes into play. So let's come back here. The problem is, what if it's too slow to query data across the network, right? Well, how slow can it be? In practice, we can serve data from the client, from the server to the client in like 1 millisecond, let's say, or maybe single-digit milliseconds in the long tail. But for some use cases, that is still too slow. So that's where DaVinci comes into play. The DaVinci client library is an alternative to what we call the classical Venice client. And it basically acts just like a follower replica. So that's why I was telling you about the details of how the follower replicas work, is because the DaVinci client is essentially running a fraction of the Venice server code, but directly in your application. So it will consume the version topic, it will populate a local RocksDB instance, and when you issue read queries to it, which DaVinci supports all of the same read APIs that I just mentioned, it will serve those queries from the local state. So it will go at the speed of your local RAM or the speed of your local SSD, which, depending on the configuration, is, let's say, 1 to 3 orders of magnitude faster in practice. So when using DaVinci, there's two different modes, basically, that you can use it in. We call them subscription modes. So you can subscribe to all the data, or what we call the unpartitioned mode. This is the easiest way to use it. And it works great for small data sets, let's say 10 gigs or less, or even like we have some applications that are going even bigger than that. But the constraint here basically is that you need to have enough local resources to hold the entire data set. So that works for small and medium data sets, but not large ones. The alternative is a bit more of a power user option, is the partitioned mode. And I'll talk more about that in a couple of slides. So some examples of use cases of DaVinci at LinkedIn include ads, the feed. The feed actually uses both like classical Venice and DaVinci in different parts of its stack. Search, which I'm going to present in more details here. So the search infrastructure that we've built at LinkedIn is essentially, we've got this collection of searchers which distribute the data among them. So each searcher has a partition of the data. And within each searcher, there are 3 types of derived data. There is the inverted index, which is used for retrieval of the documents based on some search predicate. The forward index, which contains additional attributes of the documents that have been retrieved. And finally, there's Vinci, which contains the machine learning features that relate to the retrieved documents and which are used for ranking the relevancy of these documents, right? So it's important that those 3 derived data sets are co-partitioned. Their partitioning scheme has to be aligned because shard 1, let's say, of the searcher needs to have data about the same documents, and then shard 2 needs to have data about the same documents, and so on. So this is a case where Venice is not used just as a standalone system, but rather, with Vinci, it becomes a building block of another infrastructure system. So now, let's talk about storage engines. Let's get into the nitty-gritty, right? So I've been talking about RocksDB a few times already. RocksDB is an excellent library that provides an embedded key-value store. It builds an LSM tree, basically. And it provides key-value APIs like get, put, delete, and a few others. And we use that internally quite a bit. There's a bunch of config options in RocksDB to tune it for a bunch of different workloads. The 2 main flavors that we use are block-based, which is the default storage mode. It works great when you have a data set that is larger than RAM, and you also happen to have an SSD available. Then the RAM can serve as a read-through cache for the hot part of your data, and everything else is retrieved from the SSD. If you do have enough RAM for your whole data set, then there is an even better option for that case, which is plain table, where it will mmap the entire data set and provide even better performance, and I think slightly better space efficiency as well. So we use both of these depending on the case, both in the Venice servers as well as in our Vinci use cases. Users can choose between one or the other. A little while ago, we introduced a new API in Vinci that we call the Vinci Record Transformer API, or DVRT. And what that does basically is that you can configure a closure at startup time, essentially a callback, you could say, which will be invoked by Vinci on every records that it processes. So you can use this for a couple of different reasons, right? You could change the shape of the data that lands in RocksDB. So for example, if you want to prune some columns you're not interested in to save some space, or prune some rows, essentially projection or filtering, or even do some more significant massaging or transformation of the data, you can. Or the alternative way of leveraging this is you don't even let data get to RocksDB at all, but instead you perform side effects, right? You can populate some other data structures or storage engines. If you onboard to this API, you basically get for free the support of all the Venice data sources that I presented earlier. All the batch sources, real-time sources, and hybrid are all supported kind of out of the box. So that brings me to DuckDB. DuckDB is another embedded database, but instead of being key value, it's OLAP, analytics. It provides a SQL API. It is terrific for analytics. You can do full table scans very efficiently thanks to its columnar storage format. It performs aggregation, group bys, joins, and a bunch of other things. It basically supports the full SQL dialect, I think, or close to it at least. And we have implemented a DVRT plugin for DuckDB. So what we do there is we convert the Venice schema into a SQL create table statement. And then we populate this SQL table with the Venice data. So then you get to have a SQL API on top of your Venice data. And so with this, you can see that Venice is kind of evolving towards becoming a multi-model database, right? So out of the box, you have the several paradigms of API that I presented earlier, like key value access, document store access, and limited support for vector math as well. But now with and I should say, for these paradigms, you can either use it in a stateless way, where your client queries across the network, or in a more performant, stateful way, where DaVinci will preload all the data, and you have access to these same APIs. But in addition to that, if those APIs are not sufficient, you can basically bring your own API, right? You can implement a new DaVinci record transformer, which will let you get all the data and then put it in whatever storage engine you would like, such as SQL. So all of this here on this slide is available in open source. Internally at LinkedIn, we also have some additional proprietary integrations that are not yet in open source. So we also have Venice data flowing into GPU memory, and also into a custom vector search database that we're building. So the sky's the limit, basically. And at this point, I'd like to turn it over to you and ask you, what is it that you would like to build, right? Now that you see how all these data sources are supported, how the orchestration of their merging is handled on your behalf, what other API paradigm or storage engine would you be interested in plugging in? And so if you have any ideas, let us know. All of our documentation is available at venicedb.org. From there, you can find links to the source code on GitHub, our community Slack, our social network handles. And there's also a Learn More page in the doc where you can find links to all the previous talks and podcasts and blog posts that we published. So yeah, that's all I have. Thanks for listening, and yeah, looking forward to talking to you later.